Yeah. Okay. Like, so this is network theory 203, and we had one surprise quiz. So one day again, I'm going to take same question paper again for you people, so that and I want everyone to get 30 marks someday as another surprise quiz. Same paper, no change. Okay, it's already available online, right? With the solution, it's available. Maybe I can shuffle the questions here and there, right? So this course is basically for EE students. Also, you can say it's for electronics engineering, or if somebody is in instrumentation. This is actually foundation course for many good courses like analog circuit designing, power electronics. If you want to go to filter design or signal processing, in all such courses you need to know this course, right? So it's very important, and it's like it will be prerequisite for all the courses. Without this you cannot do anything, in my opinion, right? So the course content is as follows. We have to understand that when you are learning the network theory, you have to understand following things, that you have to analyze the circuit using these many responses, like DC. Do you understand what is DC analysis? Do you know what is DC analysis and when we should do that? What is the role of DC analysis? You heard about this, right? Or no? Yeah. So when are you going to do DC analysis? Let's assume that you have some active device like this. This active device will work when this base to emitter okay. So when in this BJT there are two junctions, one is from base to emitter and one junction is from base to collector. And if base to emitter junction is forward bias and base to collector junction is like open circuit or the reverse bias, then you can have the amplification, right? And you must have seen that when it's actually forward bias, you may have voltage like 0.65 to zero point 0.7 volt, right? And then your transistor works and you can have the amplification. But all these numbers which you are seeing right now, these are the DC voltages, those are not AC. However, AC is also DC at a time. Like if you have the signal like this, if you sampled it, you can treat each of them as a DC analysis, but DC at a time, at particular time. So that's the way all the simulator works, right? So in such cases, we are going to start with the DC analysis, or we'll make sure that my transistor is in cutoff, or maybe in saturation, or in active region, right? These are the popular three region of operation. This is only possible when you are doing the DC analysis or the ID characteristic. This is also DC. So just to know which particular region it's working, you have to be you have to do DC analysis, right? So Nikita, next time please come on time. Nikita and Mahima, right? Okay. So DC analysis is very important in that case. So I believe you must have done DC somewhere. Second one is a transient. So what do you think? What should be the transient analysis?
When we just switch on the circuit, initial changes होते हैं transient.
Okay. I'll like rephrase your sentence and I'll say that anything which is with respect to time that particular analysis we are going to call it transient analysis. It may be DC, it may be like this, anything with it, which is with respect to time, we are going to call it transient. So all the simulators are going to call this kind of analysis as transient. They don't call it time response or time analysis. I'm talking about simulators, right? Third one is the AC analysis. Now that's more important thing. What do you think about AC analysis now? What is AC? You ever heard about AC analysis? So what is AC response or AC analysis? Any guess? Anything? Yeah, Nakul. Okay. Yes, Nakul. Anything? Any guess? AC. Whenever there is AC, it's associated with some frequencies. Now, can you guess something? No. Hmm? Yeah, it might be capacitor inductor, but that is also possible in transient as well as in DC. I'm saying in AC response, what kind of analysis you are doing means in transient you are, yeah, what's your name? So Anvish, with respect to frequency, if you are doing some analysis, we are going to call it AC analysis or the AC response, right? This side generally you have gain or output. Let's assume it's rather than calling gain, let's call it output. But this output we generally measure in dB. So hold on for some time. I define decibel in like 5th or 6th slides. Okay, so is there anybody who knows decibel or dB? D in small letter, B in capital. Okay. Okay. Mm-hmm. Okay. Okay. So you have some something known to decibel, but we are going to define it correct way. But before doing that, this is the grading strategy, right? So generally it's not. Okay. It's copied from some other course. That's why I kept it attendance. It was 4th year, so they don't afraid of surprise quizzes also. Right. So this is the strategy, right? So we are going to have just mid-sem and end-sem. We can take mid-sem, right? In IC courses, just we have quizzes. We have to take quiz 1 and quiz 2. DC, we can take it. So mid-sem exam, mostly after, just assume that the 21st lecture will be your mid-sem exam, as we have 42 lectures, right? So around 20 or 21st lecture, you have to tell me some suitable time. If you like Saturday, Sunday, I don't mind, right? We can have exam on that. And that exam, I generally keep open book, so you don't have to mug up the things, right? Open book you like, or you want to do it something else? Huh? Okay. Okay. Then like generally others are making some poll for open book or closed book. If you want to do it offline, you can do it and just let me know. It's same question paper. It doesn't matter. I never change the question paper. Paper is same. Right? So paper doesn't change with all these things. My checking doesn't change. It's same, right? Okay, I'll just share one thing. Like I was not teaching for last 1 year to BTech, so like my previous students can tell that. So there is a one student even in Himanshu's batch. It's civil, right? So she wrote something. Some like I asked some question, and she wrote something, and thereafter she did this one, right? But it was correct, so I gave marks. Okay. So if it is correct, I try to find out where it is correct. Okay. So do not make this cross. Okay. Always keep like it's a. I'm going to evaluate what you are doing. Even it your like rough pages also I'm going to check. Okay. So this is one thing. So you don't have any problem, right? I'll give marks if you are doing correct. Okay, but if you don't do correct, I'll not give any marks. But it's evenly distributed to all. Like if I'm giving marks to someone, means I'm going to give marks to everyone. It's like that only, right? And yeah, so there is something called spice. You must have heard somewhere. Have you heard or not? Right? IC161. Okay, you heard. Then you did some experiment also with spice or no? Okay, just you heard the word. So we are going to do some spice based simulation, and like I realized just meanwhile we are going to have something on MATLAB also. So I learned that you have never studied MATLAB anywhere. So I'll give some small things to solve. Maybe your first assignment will be with MATLAB, right? Okay. So these are the things. You agree with this? Or you want to change anything? Just let me know. Okay. So let's come back to where we were. So we are talking about AC analysis, which is with respect to frequency. You have never studied. That's why we are going to revisit it. And other than this, there is something called pole zero analysis. This is also part of AC. But in simulation, in SPICE simulation, that's a different analysis. It's known as PZ analysis. So we are going to find out where are the poles and zeros are available, and there is something called stability analysis. So all three we are going to answer it in next few days. Right? Okay, so this is a frequency response where I want to do AC analysis. When I want to do AC analysis, it's not only magnitude response. Magnitude response is the one which is output with respect to frequency. But it's also with respect to phase with respect to frequency. Combination of these two is known as Bode plot. So Bode is the gentleman who invented this, right? So there will be magnitude and phase plot both, and this is going to be used for mostly all the courses which you are going to study after this. It might be communication, it might be control. Any course you pick it up, you have to draw a Bode plot if you are interested in frequency response, right? So mostly all the things are frequency based in our electronics engineering, because generally most of our applications are communication. So in communication application, we are going to look at the frequency.
3D plot.
What 3D plot?
We combine. We have three different variables.
Okay, so in that case, still it's 2D. Generally, we draw like this. Same frequency, and there is magnitude. This is the way to draw. When you use the command like Bode of your transfer function in MATLAB, it is going to give you the combined plot like this. We'll do it, don't worry. If you want, you can do it like one by one also, like one plot here, one plot there. But doing together is very important, because you will have some information when you are going to do magnitude and phase plot together. Okay, so there are a few more terms like small signal gain. Sometimes some people call it DC gain also. Some people call it low frequency gain also. All are synonyms. You can say any name, all are same. Have you heard any one of them? Where? Yes, in BJT. So BJT, if you are drawing the frequency response, if I am drawing, let's say something like this, don't worry if you don't know how to analyze this, don't worry, it's not part of this course, right? So V out by V in is your transfer function, right, or gain. But with respect to frequency, it looks like this one. So after some frequency, the gain will be poor, and you are interested in only staying in this particular band. You are not interested in like higher band. So hmm? No, this is not it's always look from here to infinity. I want to keep my transistor inactive for sure. This is not about region. Just look at the x-axis. That's why I'm saying we are not doing DC analysis. If you are doing DC analysis, then you have to follow IC versus VCE. Looks like this one. This particular region is known as saturation. This region is known as active. This region is known as cutoff. So after fixing my transistor inactive, let's assume that I fix my transistor for given VCE. It is, let's say, some 2 volt. For 2 volt of DC, I am running frequency analysis. So I am going to change frequency of the input. So this is what I am doing. Right? Is there any doubt in these two analysis? Do not feel shy. If you don't understand, we can repeat it. But this is a very important thing. You agree with me? I forgot your name with specs. The last one, yes. Dhruv, yes, Dhruv. Do you agree with me? Almost. Okay. Very good. Okay. So this is DC plus AC. So this is what we are interested in. When I am saying that my circuit gain is around, let's say, 30 volt per volt. Right? This is what you people were doing in your laboratory, around 30 volt per volt. So that 30 volt per volt is this region, not beyond that, because that's the limitation of this circuit. You cannot go beyond this, right? Whatever plot right now I am drawing, it's also Bode plot, but it's a magnitude plot of, still it's known as Bode plot, right? So we are going to learn it, how to do it. But do you understand this? This particular gain is known as small signal gain or DC gain or low frequency gain. And when we are quoting that gain of my circuit is 30 volt per volt, means this one, from some zero frequency to higher frequency. Right? This is what we want, right? Sometimes some people call this one as bandwidth. That's the bandwidth of my BJT.
Sir, when we like in the quiz, surprises, we like while calculating the DC gain, we put the S equal to 0.
Yeah, we are going to learn it. It's part of course. Don't worry. Right now, forget about it. Yeah, wait for like few days, because I'm going to give the answer why you need to take everything outside. Right. So your question is, so the DC gain or the small signal gain is equal to 10 times 2 divided by 3 times 4, right? Yeah, that's correct. You know how to find out the small signal gain for this transfer function. No problem. But why it is happening? Yeah, when we are going to complete the understanding of Bode plot, then you will understand. Right? Hmm?
Yeah, it will be 0 because S is there.
What 0?
S equals plus 2.
Yeah, so these are two zeros. 0 and minus 2 are zeros.
Sir, when we put S equal to 0, so 10.
Yeah, but this is happening at one frequency. Like it's collectively, you have to look at everything, right? It's not only one S is going to give you the transfer function result, right? But you are right. When you are going to start the small signal gain, it's little bit lower side. We'll learn it. Okay. Okay. So, okay. All the mysterious question for you people, like order of the system. If there is a transfer function, so transfer function is for whole frequency range, I wrote something which has following things. K is the small signal gain. N of s is numerator in terms of Laplace operator. This is denominator. When you are going to write it down, you may have some s raised to m, s raised to n, right? Numerator and denominator. So we are interested in the denominator because it's going to drive your system, and that is known as the order of the system. So order of this system is n. For all the electronic circuit, remember, to make them stable, this n has to be lower than n. This solution and all these things are part of control theory. Okay, so we are not touching that right now. We are just looking at the crux of this Bode plot, and then we'll proceed further. Right? Just remember, n has to be less than m to make your system work in a proper way. There is no need to write down these things. I'm going to share this screen with you. Like, this is in the recording mode right now. Right? So I'm going to keep this also in a on Moodle so that you can directly have this lecture. Yeah. So, is there anybody who doesn't know what is the order of the system? If you have numerator and denominator, right? Everybody knows what is the order. Now, what is the pole? So, pole frequency is the one at which the entire transfer function becomes infinity at particular that frequency. So if such kind of transfer function is available to you, then I know at -1, -2 and -3 this transfer function will become infinity, right? And those are known as poles, right? And symbolically we symbolize with cross, and 0 is the frequency at which transfer function becomes 0. So you may have something like this. So order of the system is 3. There are 3 poles, -1, -2 and -3, and 2 zeros, one at origin and one is -2.5, right? So there is no problem for this. The next part, why we are doing all these things, first of all, like Bode plot, or the whole like next course which you are going to study, which is control theory. That control theory only talks about one thing: whether your system is stable or not. This is the only answer you are going to get, and for that there are plenty of analysis which you are doing. One of them is Bode plot, through which you are going to tell my system is stable or not. This is the only answer you are going to get for whole control theory. Maybe there are around 11-12 chapters, root locus or maybe polar plot, phase plot. All these plots are going to give you only one answer. You can choose any one of them, whichever you like. Some will have some limitation. Sometimes you have to use Laplace, sometimes you have to use Fourier. But in control theory, there is one assumption that the initial condition is 0, so you will not find anything other than Laplace. And they call it linear control theory. Basically, it's an adjective which is not written, but that's the thing you are going to study. Linear, just linear, which have just Laplace. So now next question is, what do you mean by stability, by the way? If the system is stable or not?
So if you give a finite input, the output should be finite.
Okay. So if I give 1 volt, output is 1.5 volt, or 1 volt input and output is 300 volt. This is finite, right? I'm writing finite numbers.
Like for a small change in input, there should be proportional change in the output.
Okay. So if my input is like this and proportional change is the incremental one, so something like this. What should I say?
I think it is
Stable. Okay. Let's define stability in another way around. If you don't see ringing, if you see ringing, it's red alert. It's unstable system. Whenever you are saying such things, those things are very bad. those things are unstable. At the output you should not see any ringing. If there is ringing, there is a problem. You can say that it's unstable system, right? This is one thing. Let's assume that this is my input and my output, one output is like this and one output looks like this one, right? So can you comment on these two, which one is stable and which one is unstable? Red is stable, right? And this is ringing, so it's unstable, right? This is also known as oscillator circuit, or this circuit which is generating this thing. This is also very important, right? Such circuits are also very important. We need it for running all digital system. So digital system all are relying on us if we are going to give them good square wave clock system, right? You must have studied clock, right? So clock is generated by the oscillator with the one fact that, okay, I told you about op amp previously, but there are three rules actually, not two, right? Two rules where V plus equal to V minus. Similarly, the current is not flowing inside or outside. Third one, do you remember? Piyush, you were with me, right? You are with me in laboratory. IC161, you are with me? Yeah. You are Piyush, right? Yeah, Piyush Bafna. Yeah, I remember. So tell me. Okay, he is also Piyush, then I'll remember Piyush now. Okay. Okay. So third one says that, okay, Divya, you remember? Is there anybody who, like, Gaurav? Gaurav, right? Your name? Yeah, or Mohit? Gaurav, yeah. So you are not responding, so I thought your name is different. Okay. Do you remember third rule? Or Nikita? I forgot your name also with stacks. Neighbor of Nikita. Yeah. Rishabh. Do you remember? Okay. If you don't remember, but this rule is applicable to all. This rule is applicable to all the circuits, which says that you can never go beyond plus V supply and minus V supply, right? So if I am designing a circuit like this, if this is 15 volt, the max output voltage available is 15 volt and I can go to 0 volt, right? So if there is an oscillator circuit or if this system is unstable, your output will be saturated at 15 volt, or let's say it's 0. So after few oscillations, this circuit this oscillations will look like a square wave. That is going to be feed as your clock, right? So this is also third rule. So remember, your output will never go beyond plus V supply and minus V supply. Let's assume that this is 10 volt and this is 0, and at the input side I am giving 1 volt, and the gain of this circuit is around 20. So what do you think the output will be? 10, right? It cannot go to 20. So if that is the problem with the saturation of your circuit, then those kind of signals are known as large signal, because your output is getting saturated. But if it is 1 millivolt, your output will be 20 milli. So if you are within the limit, all those signals are considered as small signals, and that's why, like, you are feeding always small signal input as input to your amplifier to just check output. If your output looks like this one, you must have seen something like this also, right? Because your input is very high, so it's getting saturated. So that is large signal. You cannot conclude the real gain of your amplifier. So that's why you have to do only the small signal analysis. This is one thing, right? And your circuit should not exhibit any oscillations. If they are exhibiting oscillations, means system is unstable. We don't want unstable system, we want only stable system. So there is one thumb rule, all the designer. So this is design tip I can give you. If you are a designer, you are sitting in industry, and anything, any circuit, you have to definitely check whether the system is stable or not. So just to do that, you have to remember that if there is one ring, that's acceptable. When I'm saying one ring, means output gets settled after one ring. This ring I am talking about. If it is one ring, I am going to write down something. Your phase margin, this terminology I am going to define it just later on, but phase margin will be around 60 degree. If there is no ring in your system, that's the best one, no ring, then your phase margin is greater than 60 degree. So we have to design with this number. Just remember this, it will be useful, right? And no ring means like this, right? Of course the system is sluggish, system is running very slow, but still we are going to make such system because it's stable. We want only stable system, we don't want any kind of ringing. One more thing, in first order you will never see any ringing. In first order system you are not going to see any ringing. This is the experiment I want to do on MATLAB, that if you are writing something like this, have you seen such system ever in reality? Have you seen such kind of system? No? Okay. Can you find out the transfer function of this circuit? This is V in and this is V out. So what is V out by V in? As I told you, like there is an assumption capacitor is fully discharged, it has only 0 volt at the beginning, so you can apply Laplace, no problem. So what are you going to get as V out by V in? One by, you want to write down RCS, something like this in Laplace, right? Directly you can do this, right? 1 by SC, right? Yeah, is correct, because 1 by SC divided by 1 R plus 1 by SC will give you this transfer function. It's exactly look like this one, no? This is the system I was talking about. If you remember, if you are giving square wave, the output was like this, there was no ringing. That's the best part of first order. If you are going in, or if you are increasing the order, the system will have oscillations. So as long as you are keeping your system first order, there is no problem, right? How to do that, we are going to learn it. Okay. So you know about this, as you are increasing the order, there are oscillations, all these things. Have you studied this in differential circuits, differential equations or something? Okay. Okay. I'll keep some material just to read this and just to give you why there are harmonics, right? You must have studied in terms of harmonics, right?
Yes.
Yeah, so harmonics means this oscillations, right? It's a non-linear circuit, so you have some harmonics, right? So that is what I was talking about. So this is one thing. Other than that, so stability, no problem. You should not see any oscillations. If you are saying oscillations, it's a problem. In terms of mathematically, you can say that if your phase margin is greater than 60 degree, I'm happy. because there are no oscillations. Right? Now, the next part is type of the system. Have you heard this word, type of the system? It might be new. I don't know.
Like linear, non-linear.
No, no, not not like this. In differential equation, there is one more term which is called type of the system. So we electrical engineer use very frequently. So you have to see in the denominator how many number of Laplace operator or the integrators are available. Number of integrators are deciding the type of the system. So right now it's one integrator, only one. If when there is no one integrator and there are, so this is zero type 0 system, this is type 1, this is type 2, type 3, type 4, type 5, type 6. This is useful for those people who will be in robotics. Each actually integrator is actually equivalent to something called PI controller. Yes. Right? So those many controllers you need to add. This is the meaning of that. In-depth study of this thing must be part of control theory. You will study that. But I'm just opening up all these possibility for you so that you can know all the terms. So you know all the terms associated with transfer function. There is no hidden mystery, right? You can answer all of them. Yeah.
Can you explain again this thing?
Type. Type means number of integrators. So here in denom, so in Laplace you should have studied that integration is equivalent to 1 by s, right? And derivative is equal to just s, right? So if my system has 1 by s, means one integrator is only there, so it's type 1 system. If there is two integrators, means type 2 system, or as you are increasing the number, but there is difference between order and type. Type is not equal to order. Sometimes it's yes. If the system is just only this one, means order and type both are same, right? So any doubt in all these terms? Okay, so if you agree with all these, okay. So now one more thing, this simplified form, by the way, from where I am taking all these things, it's also kept on Moodle, right? So I'm copying from there only. Somebody has wrote it a very good book, I copied that. That's the only thing. Word by word I'm teaching that. There is no change. Okay, everything is given there. Okay, it's by some Bob York. I like that, and just I, it was randomly I found him, and the theory was good. Okay, so this transfer function is also taken from there, and it says that there are lots of zeros, lots of poles, and small signal gain. And most of the time, this might be going to give you real solution or pair of complex conjugate, right? So these roots. And one more thing, if I want to make the system stable, I am going to keep all these roots, because right now in this simplified form all these roots are available at, so if you are drawing real versus g omega, then these roots are this side. Okay, now you understand what is cross and okay, cross is pole, this is pole. If I am keeping a cross, means it's pole, and this one is 0. So all the poles are this side, all zeros are this side, right? So this is called right half plane of g omega axis or real axis. So we don't like this. We want everything at left half plane. This is unstable system right now. I'm going to tell you the reason, but this system is unstable, because by observation we are seeing all of them are at right half plane. As a designer, we have to remember they have to be at the left half plane. Why? Because if you look at our previous system, something like this, which is RC, just RC, right? What is time domain, by the way, if I convert this to time, right? So if you draw this with respect to time, amplitude going towards, zero side, right? So when you are applying input voltage V in, then just V out in terms of V in is something like this, but tau is equal to R times C, right? You must have studied this in IC 160 for sure, right? So in this case, when you are subtracting V in with respect to e raised to minus t by tau, you are going to see this result, right? So there is no ringing because it's going towards zero. When you are subtracting that, you are not going to have any oscillations because they are moving towards zero, right? And that's why if we can treat each of the root and keep all of them at left half plane, there might be possibility that system will be stable. But this is the first check, right? It's a very fundamental way of doing this. If this is there, then and then you should do something else. Still your system might be unstable because look at this. This is actually higher order. As you are increasing the order of the system is actually unstable. You have to control it, right? Okay. So this is the thing, and there are few definitions of the system. If output looks like this one, or if output like this one, or you may have output which looks like this. Yellow color is visible, or yes, okay. In my screen it's not visible. Okay, so there are three possibilities. The first possibility, which I have drawn at the end, yellow color, this is called stable system, pure stable, no problem. If there are oscillations, we are going to call this kind of system as underdamped because it's underdamping situation, right? Right, and this is overdamped system. And there is one more system which is actually the best one. People uh, actually get such kind of system and they desire it with only one ring, which is at phase margin of 60 degree. This kind of thing is called marginal stable.
Why don't people prefer stable
Hmm?
without any ring?
A stable is a little bit sluggish. Look at this, yellow and red. It gets stable before yellow, right? Right. That's how there is a role of derivative control also. It's not only integral, but we are going to add derivative control and it becomes PID controller. Right? Yeah. So generally, that is the reason. Right? Okay. So you understand all these terminology. Then maybe we can talk about other things next time. Right? Okay, but before that, okay, just decibel. Decibel is there. Okay, very good. Okay, so this is also copied from same reference which I was talking about. This unit was invented by this gentleman. He was Italian and from Bell Laboratory, right? So Alexander Graham Bell. And what he is talking about, it's with the 10 base. So it's a decimal with bell, it becomes decibel. So that's how this unit came. But this unit is important in two ways. If you are working in like if you are working in normal frequency, audio frequency, but if you are working on RF frequency, RF guys like power, and we people, like I belongs to audio side, so I like voltage. So if you are interested in power, the decibel in power is equal to 10 log with 10 base P out by P in. It's a ratio always. For the case of voltage, it's 20 log V out by V, right? Do you need a, like, this is very straightforward, right? So in voltage case, it's 20, in power it's 10. And remember, like, this is the thing I am doing even other higher courses when we are going to talk everything in dB. Like I'm telling that the gain of my amplifier is 60 dB. If gain of my amplifier is 60 dB, I'm measuring in voltage. So what do you think in volt per volt? Very quick. 10 power 6 won't work. It's 120 dB. 1000, yeah, somebody told 1000, right? So it's 10 raised to 3 because 20 log, right? So you can look at this table and you have to remember few things, like 20 log 1 is 0, which is known to you. 20 log 10 is 20 dB, 20 log 2 40 dB, 20 log 3 60 dB, 20 log 4 80 dB, right? So these numbers has to be on your fingertip. When we are going to talk about it, like, you should convert it in volt per volt if you like, but we are going to talk only in dB. Some people call this one as dBV also, but dBV is equal to dB if you are taking with 20. And you have to remember few numbers like 20 log root 2, this is going to be used, so it's 3 dB. You must have heard somewhere 3 dB frequency. I'm going to use it there. That's why remember this, square root of 2, which is 0.707 in decibel, is 3 dB. This is also available, so no need to copy. Okay, 20 log 2 is 6 dB. This is also very important. If you are doubling something, I can ask you, let's say 200 volt per volt, how much in decibel? By using following things, like 20 log 2 is equal to 6 dB, right? How much is 200 volt per volt? Is it 46 dB? 46, okay, right? So you have to look at these numbers, and those numbers has to be on your fingertip. I kept one table just for your reference, right? Either you can like make it double, triple, whatever way you like, you can do these calculations, right? Otherwise, like, even if it's open book, it will not work, right? So sometimes these things has to be on your fingertip, right? Because all communication, all hardware people, all analog circuit designer, even digital circuit designers, they are going to talk only in dB. If you are associated with anything electronics, we are going to talk in dB, or something is dBm. I am not defining right now, but dBm is for power. Here it's written P out by P in, but there is one more unit for power, which is dBm. We are going to use it afterwards, but we are going to use only two units, right? Okay. So because of maybe Nikita and others, I could not complete the first part. Yeah. So please be on time because I started almost at 1:10. Okay. Okay. Any doubt? Okay. So next time we are going to start Bode plot.